In this lecture, we'll be covering the topic of parametric curves. We start with the definition. A parametric curve C in the xy plane is a pair of functions, x equals f of t and y equals g of t, that give x and y as continuous functions of t. F of t and g of t are called parametric equations. The main idea here is the parameter, in this case t, is the independent variable, and the value of the parameter gives us the values of x and y. A very natural way to think of this is if the parameter t is thought of as time, then f of t and g of t tell us where a particle moving in the xy plane is at time t. So if we start out at t equals 0, say here, and as you run the clock, you have a particle moving in the plane, we might say it's here at time 1, it's here at time 2. The xy coordinates of each of these points come from these parametric equations. So this y value here would be given by g at time 2, and here we would be at f at time 2. So recall, we're getting y from g and x from f. The parameter doesn't have to be time. It can really represent anything. But thinking of it as time is a very intuitive way to understand how parametric curves work. Let's look at an example. X equals cosine of t, y equals sine of t, and we will restrict t to be between 0 and 2 pi. To get a sense of what this looks like, note that if we take the equation for x, square it, the equation for y, square it, and add those two, we have x squared plus y squared is cosine squared t plus sine squared t, and we know that is equal to 1. Thus, x squared plus y squared equals 1. And that means we know that this is the equation of the unit circle. And that means if we think of this as the x-coordinate and the y-coordinate of a particle moving in space as the parameter, the clock, runs from time 0 to time 2 pi, this particle will move along the unit circle, because if you take the x component and square it, the y component and square it, and add those, then you get 1. So we know this thing has to be on the unit circle. Well, let's think about the trajectory of such a particle. So when t equals 0, let's look at where the particle is. If t is 0, we have x equals cosine of 0 and y equals sine of 0. We know cosine of 0 is 1 and sine of 0 is 0. So at time 0, we're at the point 1, 0. So if we think of this as a clock, the clock starts at time 0, and we begin at this point. Well, what about if we increase? Now we start letting time increase. And it looks like we're evaluating our parameter at cosine and sine. So why don't we try some more convenient radial values? So how about, say, t equals pi over 4? At time pi over 4, we have x equals cosine pi over 4, and y equals sine pi over 4. And we know that these values are root 2 over 2. And so at time pi over 4, that is our point. Root 2 over 2, root 2 over 2, which puts us about here. And we can keep doing this. If we do, say, time pi over 2, then we have x equals cosine pi over 2, and y equals sine pi over 2. We know cosine pi over 2 is 0, and sine pi over 2 is 1. So this gives us the point 0, 1 here at time pi over 2. And what we notice is that this parametrization has the particle moving counterclockwise along the circle. So we start out at time 0, time pi over 4, time pi over 2. We could probably guess that at time pi we'll be here, and we can check that. So when t equals pi, we have x equals cosine of pi, y equals sine of pi, and we know that sine of pi is 0, cosine of pi is minus 1. So we get the point minus 1, 0. At time pi. And we go all the way until the final time, which is 2 pi, and we see at time 2 pi x is cosine of 2 pi and y is sine of 2 pi. And we know that cosine of 2 pi is 1 and y of 2 pi, sine of 2 pi, is 0. So we're at the point 1, 0. And so we end where we began, and we see that, yes, in fact, this is a parametrization of the unit circle. This parametrization traces out the unit circle exactly once in a counterclockwise direction, starting at the point 1, 0. Let's look at a second example where we have x being 1 minus t squared over 1 plus t squared, and y is 2t over 1 plus t squared. But this time our parameter ranges over the whole real numbers. And let's try the same approach. Let's square x and square y and add them and see what happens. So in this case, x squared plus y squared is equal to the quantity 1 minus t squared over 1 plus t squared, all squared, plus the quantity 2t over 1 plus t squared, all squared. Foiling out the numerator here, gives us a 1 minus 2t squared plus t to the fourth. Squaring the numerator in the second term gives us a plus 4t squared. And we have a common denominator of 1 plus t squared, the quantity squared. And now notice that these terms here combine, and this gives us 1 plus 2t squared plus t to the fourth over 1 plus t squared squared. And what we notice is that the top can be factored as 1 plus t squared squared. And we see that what we actually have here is 1. Thus, for any value of the parameter t, when you take the x-coordinate and square it, take the y-coordinate and square it, and add them, you get 1. So this again means that this must be on the unit circle. Again, because x squared plus y squared equals 1. Let's now consider examining what the parametrization actually looks like. So we know, again, as in the case before, that this curve has to at least be on the unit circle. And so let's think about where we are at time 0. So at time 0, our x is 1 minus 0 over 1 plus 0, or 1. And our y is 2 times 0 over 1. Or 0. So we're at the point 1, 0. So at time 0, we start out here. How about at time 1? At time 1, our x we have 1 minus 1, or 0, over 2. So x is 0. Y is 2 times 1, or 2, over 1 plus 1, which is 2. And so we're at the point 0, 1. And what this looks like is a parametrization where we're moving, again, counterclockwise along the unit circle from the point 1, 0 to the point 0, 1. But this gets interesting because if we think about what happens as we continue to increase t, if we think about the limit, as t goes to positive infinity, because remember, this time our parameter t varies over the entire real line. As t goes to infinity, we see from our knowledge of limits that because the dominant terms, we have the dominant term in the numerator of negative t squared, and the dominant term in the denominator of t squared, we know the limit of x of t is -1. And the limit as t goes to infinity of y of t, in that case, the dominant term in the numerator is 2t. The dominant term in the denominator is t squared. The ratio of the dominant terms is thus 2 over t. So as t goes to infinity, y of t is going to 0. So what this means is that as the parameter t is approaching infinity, we're approaching this point, -1, 0. So this parametrization, you can think of it as we're moving counterclockwise along the top of the unit circle. But really think of it as if t is your clock, you're slowing down, and you in fact never actually get there to this point, because you would need an infinite value for t. You would actually need to get to that limit to get to the point -1, 0. So we see we parametrized the top half of the unit circle, but we've only gotten half the story, because recall, our parameter has domain the entire real line. So we need to think in terms of going the other direction, if t goes negative. So what if t is equal to -1? If t equals -1, we go here and we see our equation. We still get a 1 minus 1, or 0, over 1. So we get an x value of 0. And y, in this case, we get a -2 in the numerator and a 2 in the denominator. And so we get a -1. So we're at the point 0, -1. So at time -1, we're at this point here. And we actually end up with a similar result because the limit as t goes to -infinity of our x of t going to -infinity, we still have the -t squared in the top and the t squared in the bottom as the dominant terms, and the t's are both raised to an even power. So going to -infinity will not be a different result than if we were going to + infinity. The ratio of the dominant terms is -1, and so we will get -1. When we look at the limit as t goes to -infinity of y of t, we again make the argument that the dominant term in the top is 2t. The dominant term in the bottom is t squared. So the ratio of dominant terms is 2 over t, but our t is negative. So it's important to recognize that this is going to 0, but it's staying negative, which puts us down here. The y of t is always negative in this case when t is negative. So what happens is our parametrization for negative values of the parameters take us clockwise around the bottom half of the unit circle, approaching the point -1, 0. as t goes to negative infinity. But again, you want to think of it like the parameterization works in this way where it's going fast and then it slows to a crawl and takes an infinite amount of time to get to the point. -1, 0, but it never actually gets there. So this is another example of a way to parameterize the unit circle, although we missed this point. One final example is as follows. X equals root t, y equals 3t minus 2, and we work for t greater than or equal to 0. And the idea here is we note that if we work with the first equation, we can solve for t. So let's take that equation and square both sides. And we get x squared equals t. But that means this t can be substituted in to the second equation. And so we get y equals 3x squared minus 2. And we know exactly what that looks like because (3x squared minus 2) is something we know how to graph. But we're only working for t greater than or equal to 0, which would mean x greater than or equal to 0. And what we've done here is a process called eliminating the parameter. And you can see that you can go back, if you can eliminate the parameter, we can go back to writing things y as a function of x. You can also go the other way. If you're given a function written y equals f of x, we can write this as a parametric curve simply by saying let x equal t and then y equals f of t. So you can think of parametric curves as a generalization of the way that we know how to represent curves when we write them y as a function of x. And this will come in handy because anytime we talk about curves in calculus, we want to talk about the case when they're smooth and the case when we can take derivatives. And that will be the next lecture.